Hello everyone, welcome to week 3 live session of NPTEL's Introduction to Semiconductor Devices course. I'm Om Maheshwari and today we'll be solving some questions that will help you with your assignments as well as your exams. So let's start. So in this week, we'll mostly focus on the questions related to carriers under electric field, mobility, drift current, diffusion current, and energy band diagram related questions. Before starting, let's take a quick recap at the content that has been taught in the videos this week. So this is a very brief overview. I highly recommend that you watch all the video lectures before solving your assignments. First is the about the interpretation of the energy band diagram. So it says when electric field E exists inside a material or applied as an external stimuli, the band energies EC and EV become a function of position. The resulting variation of EC and EV with position of band diagram is popularly known as band bending. It serves as a powerful tool to interpret the electric field, electric potential, kinetic energy, potential energy of carriers, carrier density N, P in the semiconductor by mere visual inspection. The following formulation provides a means of readily deducing the electrostatic variables associated with band bending. So what they are trying to say is in a semiconductor band diagram, if there is some bending in the bands, you can deduce multiple things from it. You can find out the electric field E, you can find out the concentrations N and P. You can find out the potential energy and kinetic energy also just by looking at the band diagram intuitively. So potential energy E is given by the potential energy P is given by minus QV, which is EC minus E ref. So if there is any reference point, the potential energy at every point is the difference of EC and E ref. Electrostatic potential is just minus 1 by Q of P. And the electric field E is given by the derivative of the energy band. The derivative of energy band gives us the electric field. It is E is equals to 1 by Q dEC by dx. So 1 by same as dEV by dx and dEI by dx because all whether it be EC, EI or EV, all have same slope. That's why electric field can be calculated by any of these. Further, if you try to solve this in terms of grouping, then E will be given as 1 by Q, 1 by N, del N by del X. This is another relation which can be found just by substituting the values of EI here, such as KT by Q, ln, sorry, KT, ln, N by Ni. And if you substitute it here and then uh, this will be EF minus EI, write it here. EF minus EI will be KT ln N by Ni. So del, if I take derivative of this, I'll just have del EI by del F, del X equals to minus KT 1 by N, Ni by N, del N by del Ni, del N by Ni upon X, del X. This gives us this. Okay, please feel free to ask any question when you have any doubts. You can either type in chat or unmute yourself and ask. All right, so next is the minority carrier diffusion equation, MCDE. So diffusion simply means the migration of the particles from high concentration to low concentration due to random thermal motion of the carriers. MCDE is a partial differential equation in space and time depicting the evolution of carrier action when semiconductor system is perturbed. It is derived from the continuity equation under the following assumptions. First is the system under analysis one-dimensional. Analysis is restricted to minority carriers. Electric field is zero in the semiconductor. Automation is mostly photo generation of carriers. Low-level injection conditions prevail, such as delta P is less than the baseline and zero for N-type semiconductor, and delta N is less than the dome P0 for the P-type semiconductor. And these are the minority carrier diffusion equations. Del of delta N in P type by del T. So this NP means this N is the minority carrier in a P-type semiconductor is equals to dn d2 delta N by del X minus delta N by tau plus GL. Similarly for the P. Then we have the diffusion length, the minority carrier diffusion length. The diffusion length whereas excess carrier concentrations falls off exponentially to 1 by E so that of that to the point of injection is termed as minority carrier diffusion length. It is given as LP is under root dp tau p. dp is your diffusion constant. Similarly, ln is under root dn tau 1. So again, there should be a focus on minority. Since it's a minority, it will be n-type semiconductor. This should be p-type semiconductor. Since holes are minority in n-type semiconductor and electrons are minority in p-type semiconductor. Another concept is quasi-Fermi levels or energy. These are the energy levels used to specify carrier concentration inside semiconductor under non-equilibrium. So Fermi level in a semiconductor is only defined for equilibrium. And equilibrium means Fermi level will always be constant. But in most real cases, when a semiconductor device is under operation, those conditions are often non-equilibrium conditions. So under these conditions, uh, the the carrier, by definition, they are related to the non-equilibrium carrier concentration in the same way EF is related to equilibrium carrier concentration. The quasi-Fermi level for electrons and holes are given as follows. So they are similar to the Fermi level. They have similar definition. They tell you the same thing like how is doping varying, but under the non-equilibrium condition. Okay, so I hope you all have gone through the lectures and already know these concepts. If there is any doubt, please do let me know. Let us start with the questions now. So the first question is, according to Einstein's relation, for any semiconductor, the ratio of diffusion constant to mobility of carriers, option A, depends on the type of semiconductor, B, varies with the lifetime of semiconductor, C is a universal constant, D, depends upon the temperature of the semiconductor. Please let me know your answers. Okay, so option D is correct. It depends upon the temperature of the semiconductor. So the Einstein solution is dn d by mu is kt by q. This is the Einstein relation where d is the diffusion constant, mu is the mobility, and T is the temperature. So the Einstein relation is dependent on the temperature. That's the option D is correct. Michaela, can you be please more specific? Like what do you exactly, what is your doubt in it? What do you mean by semiconductor and electric field? What is your doubt exactly? The change in band diagram with respect to that. Okay, so to understand this, so first of all is like let's talk about the internal electric field. And you have not applied any external source. So here it's not like electric field is changing your band diagram. It's the opposite. The change, the your different doping concentration, it leads to change in your band diagram, which gives us different electric fields. Right. So let's say so we'll okay, we will see Fermi level also in this. So let us say you had a n-type doped, let's say an intrinsic semiconductor, this EC, this EV. So electric field is del EC 1 by Q del EC by del X. Here EC is constant, so electric field will be zero. Let's take a case 2. Here, let's say del N by del X is there. There is some change in concentration. So in equilibrium, if I see Fermi level, as I said, will always be constant. So I'll draw Fermi level first. Now let's say dF by dx is uh, such that uh, from electron concentration increasing from left to right. Okay, let's take this in this case. Electron concentration is increasing from left side to right side. So what will that mean? Let's say this is your semiconductor. Electron concentration is increasing like this, right? From left side to right side. So what will happen to the band diagram? It will look something like this. This is EC, this is EV, and EI will also be something like this because EI is always in the mid band gap. Okay, so why this? We already know, right? When concentration is high, then EF is closer to EC. When concentration is low, EF is farther from EC. So Fermi level difference between Fermi level and EC tells us how much doping is there. If EF and EC are very close, that means very high doping. Okay, so now I can see there is a slope in these bands. Then there will be some internal electric field also, and that internal electric field will be from here to here. Is this clear? Okay, then could you please be more specific? What is the exact question? Well, I think we have this question. Let's see. Can you share the figure also? Without figure, I cannot understand. Okay, so I also have similar questions. We'll go through them. If you still have doubt, you can ask again at the end of the class. Okay. Okay, any doubt in what we discussed here in this part? Okay, I'll get to the next one then. The next question is, if the mobility of the carriers in an n-type semiconductor is 480 centimeters square per volt, then what is the diffusion length of the minority carriers within the semiconductor? Assuming minority carrier lifetime is 10 microseconds. Okay, option C is correct. So how do we solve this? We know that in magnetic carrier, the in n-type emitter, the magnetic carrier will be p-type, right? So LP is equals to under root dp tau p, and dp is equals to mu kt by q, which is 480 into 0.026. So here I'll substitute it under root 480 into 0.026 into tau p is 10 into 10 to the power minus 6. So when we solve this, we get 0.01117 centimeter, which is 111.7 micrometer. So answer is option C. The closest one is 111.5 micrometer. Okay, let's look at the next one. Assume the donor concentration in an N-type semiconductor at the end is given by this, where L is this. Determine the induced electric field in volt per centimeter at x equals to 10 to the power minus 4 centimeter. Please try to solve this. The concept involved is similar to what we just discussed in the review. So we'll have to use this. So it just tells you how electric field changes with change in concentration of the semiconductor. So you have to use this equation equals to 1 by q, 1 by n, del n by del x. So this is kt by q, not 1. Okay, do we have an answer for this? Yes, option B is correct. So 1.29. So let's see how this is solved. Okay, we know this. So ND is given as 10 to the power 16 e to the power minus x by L. So del ND by del x will be 10 to the power 16 minus 1 by L e to the power minus x by L, right? Which will be same as del ND by del x will become minus ND by L, right? This is ND. 10 to the power 16 minus x by L is ND. So our electric field E is KT by Q 1 by N del N by del X, which is KT by Q 1 by ND, and del ND by del X is minus ND by L. So ND and ND will cancel. We will have KT by Q minus KT by QL, which is 0.026 by 2 into 10 to the power minus 2 is the L, which will give us minus 1.295 volt per centimeter. Answer is option B. Okay, so this this question is clear to all. All right, so let's see the next one. In an n-type semiconductor bar, there is an increase in electron concentration from left to right. An electric field exists pointing to the left. So we have a semiconductor bar and concentration is increasing of n-type from left to right. This is N, and an electric field points axis pointing to the left. So electric field is in this direction. If we double the electron concentration everywhere, what will happen to the diffusion current and drift current? So let's say this was the profile of N. This N becomes 2N. Then how will J drift and how will J diffusion change? Yeah. So we know that. So option B is correct. Both will become double. Why? Because J drift is NQ mu E and J diffusion is minus Q D del N by del X. So here we have N. This N will change to 2N. Here this N will change to 2N. So definitely J drift will become 2X. But here this is becoming 2N. Will electric field change if this gradient becomes this? What will happen to the electric field? Here Q is constant, mu is constant, N is doubling. What happens to E? Will it also double? Right, electric fields remain same as we just saw, right? E is 1 kT by Q, 1 by N, del N by del X. So if this becomes 2N, this also becomes 2N, and these 2 and 2 will cancel. So electrical remains same. So this J drift will also become 2X and both become double. Okay. All right. So let's move on to the next one. Consider a hypothetical energy band diagram as shown in figure 1. Sketch the electric field E as a function of X best described by. So this is your energy band diagram which is shown in the figure, and you have to tell among these four options below which one correspond to the distribution of electric field for this particular band diagram. Okay, so let's see how do we solve this. So in this question, we are given this band diagram, right? And we know electric field E is 1 by Q del E PC by del X, right? So electric field is described by the slope of the conduction band, right? So here the slope is here the conduction band is constant. So that means definitely here E will be 0. So let's draw it step by step. Let's say this is EC with some, let's say with respect to some reference. EF is the reference. So we are drawing electric field. So here in this part, it will be 0 because EC is constant. Here in this part, EC is decreasing. So del EC by del X will be negative, right? So here it will be negative 0, here it will be negative. Similarly, here also EC is decreasing, right? With X. So del EC by del X here also will be negative. Here del EC by del X equals to negative. So your electric field will also be negative. So this is your final profile of electric field E. Okay, so this option is option A. Is this clear? Okay, if you want to see about hole or electron concentration, that's also easy here, right? So let's say I'll draw this again. This is EC, this is EF, right? Now we want to let's say talk about how N is changing. Okay, so let we know that N equals to KT of Ni e to the power EF. Okay, let me write it. EF minus EI by KT. Right, this is the expression of N, or we can also write it as um, N equals to NC e to the power EC minus EF by KT. Okay, so not EC minus EF. Yeah, EC minus EF. Yeah, actually, yeah. Okay, let's not confuse ourselves. I'll only use the first one. Yeah. Here I'll draw EI also. EI is something like this. Okay, this is EI. Now you see, we have N varies proportional to exponential of EF minus EI, right? So here EF minus EI is very small. Here it becomes constant, and here it increases further. So what it means is your electron concentration here exponentially increases, then becomes constant, then increases exponentially again. Okay, I'll draw with another color. Here it exponentially increases from 0, then becomes constant, then increases again, right? Because it is proportional to exponential of this distance. Is this clear, Makela? Yeah. So if there are no more doubts in this question, we can move on to the next one. So for questions 6 to 9, now we'll have to take these informations. First is calculate the drift current density. Okay, so here what we have is we have to find drift current density. You know that J drift NQ mu E. So it will be N is 2 into 10 to the power 15, Q is 1.6 into 10 to the power minus 19, mu is 1200, and E is 400 volt per centimeter. So if you solve it, you get 153 ampere per centimeter square, which corresponds to option C. Is this clear? Okay. Next one is calculate the diffusion coefficient dm. So these are the numbers. I'll write them again. Mu1 is 1200, and kT by Q is 26 millivolt, and it's 2 into 10 to the power 15 per centimeter square per centimeter cube. E is 400 volt per centimeter. Del N by del X is 2 into 10 to the power 20 per centimeter cube. We must use these values in this question also. Please find the diffusion coefficient. Okay, so what is the answer? So we know that dn upon mu1 is kt by q. So dn is mu n into kt by q, which is 1200 into 0.026, and we do that calculation, we get 31.2, right? The answer is option A. Okay, Mikala, you're right. Like they have been given both this and this, so both cannot be there. But it's just a numerical question. So for this, we'll take this value. Anyways, for calculating this part, we don't need neither this nor this. Okay, so next one is calculate the diffusion current density. So we have to find J diffusion. Okay, so J drift is, so J diffusion is minus Q dn del n by del x. That is 1.6 into 10 to the power minus 19. dn we calculated 31.2 into del n by del x is 2 into 10 to the power 20. So if we calculate it, we get minus 998 ampere per centimeter square, which is option C. Okay, all right. The last one is calculate the total current density. You know that total current is J drift plus J diffusion. This was 153 plus minus 998, right? So we'll get 845 ampere minus 845 ampere per centimeter square. So option C is clear to all. All right. So if there are no doubts in this, let's move on to the last question. In a semiconductor, the minority carrier concentration profile is given by the formula this. Which of the following statements is true? Statement 1, the longer diffusion length L reduces in a slower decrease in minority carrier concentration with distance. Statement 2, longer diffusion length L results in a faster decrease in minority carrier concentration with distance. So, if both are contradictory, only one of these can be correct. So, it's either statement A or statement B. Please see which one is correct. It's a mathematical question. The question is when L increase, what happens to delta N by what happens to delta N? Either it increases or decreases. Right? It will decrease, right? So this statement is correct, which means option C is correct. Okay, so I'll pause here. So if you have any doubts till now or any other doubts, We can discuss them in any of these questions, or if you have any doubt in any other concept till now, we can discuss. Okay, so let's see assignments 9 question. Give me a minute. I'll open the assignment. Okay, so this is the assignment and question 9. So the question says, okay, so what is the doubt in this question, Rumi? It has multiple answers. Okay. All right. So you have option to choose only one. Uh, okay. So what we can do is maybe you can choose any of one of the correct ones. I'll report it to the NPTEL team and we will get this question reviewed. If like if there are multiple answers, the question will be you will be given full marks. You can choose any one of the correct ones now. Okay. Okay. And Kala has in assignment one question. Let's see. Silicon sample maintained at 300 Kelvin. Uh, I don't see this question in assignment one. Nikala. Okay, first assignment question number one. Okay, week three. Okay, this question. A silicon sample is maintained at 300 Kelvin, characterized by energy band diagram shown in figure. Consider EF as resistor reference level. Suppose it denotes the hole concentration at this. This is what can I say about the hole densities? Okay, so let's see. This is very similar to the question we already solved, right? So we solved this question. It is very similar to this question. So let us see this one. Add a page here. The band diagram is like this. This is 0. This is L by 2. This is L. And this is X. The question is, at X equals to 0, the whole concentration is P0. Here it is PL by 2. Here it is PL. So we have to tell the relation between these, right? So I think it's very simple question. We just need to see the distance between this is EV. We just need to see the distance between EV and EF. When it's closer to EF, that means EF closer to EV means more volts, right? So you can simply see that right here at P0, this is further. This means P0 is the lowest. And here in both of these, this is same. So these two should be same. So that sequence should be P0 less than PL by 2 equals to PL. Is this clear, Nikala? Yeah, y-axis is obviously energy. If it's band diagram, it is energy. In band diagram, you always have y-axis energy, x-axis as position. Okay, is there any doubt in this further? Is the doubt clear? You just have to see this, right? Actually, in question, this is almost same. I have drawn it like this. It's my bad. But yeah, these are same in the question. These two at L by 2 and L. It's my drawing fault. It's curved till here, then constant here. It's curved here and then constant in this part. So this EF minus EV does not change. The diffusion, which question is that? The diffusion constant question. Please name. Yeah, it will be much less. That's okay. Question number 6. Let me look at question number 6. Which of the following option describes correctly the equilibrium band diagram? Okay, P and N plus P double plus. So this is simple question. Question 6 in assignment third. So what is the problem in question 6? Yeah, in my discussed question, what is the problem? The electron concentration is a gradient. Okay, so electric field varies. Okay, yeah, it affects VD. Sure. So I think you are getting confused. See, this band diagram is in equilibrium, right? So there is no net current flow. And simply you have been asked at this point, and at this point, what is the hole concentration? That we can directly tell by difference between EF and EV, or if you want, you can see between EF, EI and EF also. What does it have to do with VD and field? The concentration is not changing at this point, and this point. So our answer still would be this only, right? What is the doubt I'm not getting? Okay, is there anything else? I cannot unmute you. You have to unmute yourself, I think. There's no restriction on opening the mic from my end. It's not allowing me to unmute you. Are you not able to unmute yourself? Uh, Let me check the settings. I don't think there is any restriction on the microphone. Mekalam, if you want, you can maybe rejoin. I'll wait here for a minute then. Yeah, please join again. I'm waiting. We can discuss them. Okay, are you able to unmute now? Okay, anyways, if there is difficult to type in chat, you can maybe send me an email later. My email ID is uh, this. So if you have any doubts, you can share it over the email with pictures and whatever you can. Okay, is there anything else? All right, then we can close the session for today. If you have any doubts, please send me an email. I'll go through it. We can discuss over there. Thank you. See you next week.